Hello everyone, welcome back to my channel. In our last video, we talked about the three main techniques of differentiating functions, which were the chain rule, the product rule, and finally the quotient rule. Today, however, we will be focusing on a special set of functions, which are the trigonometric functions, also known as the sinusoidal functions, like y equals sin x, cos x, tan x, and etc. Before we jump right into the calculus part though, I believe it's important to have a good idea about the functions themselves. For example, if we have a right angle triangle ABC where angle ACB is theta and angle BAC is alpha, then according to the formula, sin theta will be equals to opposite by hypotenuse, and cos theta, which is 1 by sin theta or its reciprocal function, will be hypotenuse divided by opposite. Similarly, for cos theta, we have adjacent by hypotenuse, and sec theta will be equals to 1 by cos theta reciprocal function or hypotenuse by adjacent. And for tan theta, we have opposite by adjacent or sin theta by cos theta, whereas cot theta, its reciprocal function is 1 by tan theta equals adjacent by opposite or cos theta by sin theta. Similarly, for alpha, we have sin alpha equals to adjacent by hypotenuse, cosec alpha equals hypotenuse by adjacent, cos alpha equals opposite by hypotenuse, sec alpha is equals to hypotenuse by opposite, and finally tan alpha is equals adjacent by opposite, and cot alpha is equals to opposite by adjacent. As alpha is equals to 90 minus theta, or alpha plus theta plus 90 equals to 180 degree, which is the sum of angles of a triangle, we have sin theta equals to cos alpha or cos 90 minus theta, and cos theta equals sin alpha equals to sin 90 minus theta, and finally tan theta is equals to cot alpha or cot 90 minus theta. And now let's move on to the graphs of the trigonometric functions. For example, in sin x graph, we have a maximum value at 90 degrees for the value of 1, and at 270 degrees we have the minimum value of -1. For cos x, we have the maximum value at 0 and the minimum value at 180 degrees. For the graph of tan x, we don't specifically have any maximum or minimum points, but rather we have a point of inflection at 180 degrees. For cosec x, we have a minimum point at 90 degrees and also a maximum point at 270 degrees. For sec x, we have a minimum point at 0 degrees and a maximum point at 180 degree, as well as a minimum point on 360 degrees. For cot x, which is the reciprocal function of tan x, we also have no specific minimum or maximum points, but rather a point of inflection at 90 degrees and 270 degrees. Now, before we find out the differentiation of trigonometric functions, let's look at some trigonometric formulas. Here we have the four main formulas, which are also called the compound angle formulas. For example, sin A plus B is equals to sin A cos B plus cos A sin B, and sin A minus B is equals to sin A cos B minus cos A sin B. For cos A plus B, we have cos A cos B minus sin A sin B, and cos A minus B is equals to cos A cos B plus sin A sin B. So applying sin A plus B plus sin A minus B, we get 2 sin A cos B. Let x is equals to A plus B and y equals to A minus B. So we have x plus y is equals to 2a and x minus y is equals to 2b. Hence we have the factor formula, sin x plus sin y is equals to 2 sin x plus y divided by 2 multiplied with cos x minus y divided by 2. Similarly, for other ones, we also get sin x minus sin y is equals to 2 cos x plus y divided by 2 multiplied with sin x minus 2 whole divided by 2. For cos x plus cos y, we get 2 cos x plus y divided by 2 cos x minus y divided by 2, and cos x minus y is equals to minus 2 sin x plus y divided by 2 multiplied with sin x minus y divided by 2. So now let's move on to the differentiation of trigonometric functions. If you remember from our first video where I have shown you how you can differentiate from first principles using the formula dy by dx is equals to limit of h tends to 0 function of x plus h subtracted with function of x whole divided by h. So when function of x is equals to x, so when function of x is equals to sine x, we have dy by dx is equals to limit of h tends to 0. Here we have sine x plus h subtracted with sine x whole divided by h. And if you remember one of the formulas where we had sine x minus sine y, we had 2 cos x plus y divided by 2 and then sine x minus y divided by 2. Just a reminder of the formula. Here is our required formula. So continuing with our calculations, we have limit of h tends to 0, and using this formula we have 2 cos x plus h plus x and divided by 2, then multiplied by sine x plus h subtracted by y, which is x, divided by 2, and then whole divided by h. And continuing with our calculations, we have limit of h tends to 0. Here we can simplify by adding the x. We get 2 cos 2x plus h whole divided by 2, and here the x terms gets cancelled out, so we have only sine h by 2 and whole divided by h. So for calculus, you have to remember a very important limit, which is limit of x tends to 0 sine x divided by x is equals to 1, where x must be in radians. So from this expression, we actually get the small angle approximations of sine x is approximately equals to x, given that x is very small and measured in radians. So rearranging the expression, we get cos 2x plus h whole divided by 2 and then sine h by 2 divided by h by 2. So finally, now we have the given expression in the form of the limit that we initially wanted, which is sine x by x. So applying the limit, when h is equals to 0, cos 2x plus 0 divided by 2 becomes cos x simply. And here for sine h by 2 divided by h by 2, using this logic, you can say that the limit becomes 1. So finally we get cos 2x plus 0 whole divided by 2 multiplied with 1, and basically we get cos x. So therefore we have proven that the derivative of sine x or d dx of sine x will be cos x. So now let's apply the same kind of principles for cos x. So using the same fundamental formula for the differentiation from first principles, we have when function of x equals to cos x, then dy by dx will be equals to limit of h tends to 0 of cos x plus h subtracted with cos x whole divided by h. Now if you remember the fourth formula, the factor formula of the trigonometric expressions, where we had cos x minus cos y is equals to minus 2 sine x plus y divided by 2 multiplied with sine x minus y divided by 2. So just for reference, we have cos x minus cos y is equals to minus 2 sine x plus y divided by 2 and multiplied with sine x minus y divided by 2. So here we assume that x plus h is x and x it becomes y, so we have minus 2 sine x plus h plus x, which is x plus y, and then divided by 2 multiplied with the sine of x plus h subtracted with x, which is x minus y, and then divided by 2, and then whole divided by h. So further simplifying, we get limit of h tends to 0, and then x plus x will be 2x, so we have minus 2 sine 2x plus h whole divided by 2 and multiplied with sine x plus h minus x, which is simply sine h by 2, and then whole divided by h. So doing the same exactly like the previous one, we have limit of h tends to 0 minus sine 2x plus h divided by 2 multiplied with sine h by 2 divided by h by 2, and we exactly have the similar kind of format here. So applying the limit, we have sine 2x plus 0 divided by 2 and multiplied with 1. As I mentioned previously before, the limit of sine x divided by x, given that x tends to 0, will make the expression tend to 1 as well. And finally simplifying, we get sine x, as 2x divided by 2 is 1, so we get x here. And just like that, we have proven that the derivative of cos x will be minus sine x. And finally, let's move on to the differentiation of tan x. So when function of x is equals to tan x, we have dy by dx is equals to limit of h tends to 0 tan x plus h subtracted with tan x and whole divided by h. Now for the differentiation of tan x, we don't necessarily have to use any of the factor formula. Rather, we have to use one of the most important trigonometric identity, which is tan x equals to sine x divided by cos x, as I previously mentioned in the diagram before here. So applying the formula, we have limit of h tends to 0 sine x plus h divided by cos x plus h subtracted with sine x divided by cos x and then whole divided by h. Further simplifying, we get limit of h tends to 0, and here we have to combine the fractions. So therefore we multiply the left side with cos x by cos x, which is cos x multiplied with cos x plus h, so that we get the same denominator, and at the top we have cos x multiplied with sine x plus h, and we have subtracted with sine x multiplied with cos x plus h, because the right side needs to be multiplied with cos x plus h divided by cos x plus h, so that the denominators are same, and we have cos x multiplied with cos x plus h. So further signifying, up at denominator we have cos x multiplied with cos x plus h, and as the numerator we have cos x sine x plus h subtracted with sine x cos x plus h. divided by h. And now if you remember one of the addition formulas, this is exactly in the format of sine a minus b, where if you remember sine a minus b was equals to sine a cos b minus cos a sine b, or cos b sine a minus sine b cos a. So assuming this is b and this is a, we also get the similar case for b and a. Therefore we can express this whole expression as sine a minus b, and so we get sine x plus h minus x divided by cos x multiplied with cos x plus h and whole divided by h. So continuing with our working, we have limit of h tends to 0. Simplifying this, we have only sine h divided by h, which is this term, multiplied with 1 by cos x multiplied with cos x plus h. So if you remember one of the most important limits in calculus, that limit of x tends to 0, sine x divided by x will be equals to 1. So here we have the same case, and we can write that as being 1 multiplied with cos x, and as h is 0, it simply becomes cos x. So we have 1 by cos square x, or simply written as sec squared x. And thus we have proved that ddx of tan x is equals to sec squared x. And applying the same kind of technique for the other remaining reciprocal trigonometric functions, we have ddx of sine x is equals to cos x. For ddx of cos x, we have minus sine x. For ddx of tan x, we have sec squared x. For ddx of cosec x, we have minus cosec x multiplied with cot x. For sec x, we have sec x multiplied with tan x. And lastly, for cot x, we have minus cosec squared x. So now let's move on to some exercises. For number 1, we have to find out the derivative of 3x squared tan squared x plus pi. So if you have watched my third video about the product rule, where you have ddx of u multiplied by v, you have u multiplied with dv by dx plus v multiplied with du by dx, and here so we have 3x squared multiplied with the derivative of v, which is tan squared x plus pi. So we write that down, tan squared x plus pi plus tan squared plus tan squared plus tan squared x plus pi So applying the product rule formula, we have 3x squared multiplied with the derivative of v, which is tan squared x plus pi, plus v into derivative of u, which is tan squared x plus pi multiplied with the ddx of 3x squared. Now differentiating them, this will be the same, 3x squared, and multiplied with the derivative of this. So we have to apply the chain rule to tan squared x plus pi, assuming this is a separate function u. So we have 2 multiplied with tan x plus pi, which was considered the separate function u, and then multiplied with the derivative of the initial function, which we considered as u, which is tan x plus pi, and then plus the rest of the guy, which is tan square x plus pi multiplied with the derivative of 3x squared, which will be 6x to the power minus 1, which is 1. So I'm not writing down the power. So continuing with our workings, we have 3x squared multiplied with 2 tan x plus pi multiplied with the derivative of tan x plus pi, which is sec squared x plus pi, if you recall the formulas given here. And then plus we have 6x tan squared x plus pi so further simplifying, we have 3 multiplied with 2 to get 6x squared, then tan x plus pi multiplied with sec squared x plus pi plus 6x tan squared x plus pi, and this is our final answer. So for number 2, we have to find the derivative of 1 plus 2x sine 5x divided by x. There are mainly 2 ways of doing it. One is by using the quotient rule, as this is in the form of u by v, or we can simply simplify it to get 1 by x plus 2 sine 5x, as 2x divided by x is 2. So writing 1 by x in its power form or index form, we get x to the power minus 1 plus 2 sine 5x. Now differentiating, we get minus 1 multiplied with minus 1, which is minus 2, plus 2 multiplied with the derivative of sine 5x. Now if you remember that the derivative of sine x is cos x, so therefore it will be cos 5x. Just because you assume that this initial function was u, therefore you have to multiply it with the derivative of the inside function, which is 5x, just like in chain rule, and finally we get minus 1 by x squared plus 2 multiplied with 5, as differentiation of 5x is 5, so we get 10 cos 5x. So for number 3, we have to find out the derivative of 2 cos 4x subtracted by 4 cos x plus 2 cos 7x. Now if you remember the derivative of cos x, which is ddx of cos x, being minus sin x, so differentiating we get 2 multiplied with the differentiation of cos 4x, so we have minus sin 4x. Now as before, because we have initially assumed that this is x, therefore we have to multiply it with the derivative of 4x, the inside function, and minus 4 into minus sin x, as the derivative of cos x is minus sin x, and then plus 2 multiplied with minus sin 7x, and then again differentiating with 7x according to the chain rule. So we have 2 here and we have 4 here, so we are at minus 8 sine 4x. As there are 2 minus signs here, we get plus 4 sine x. And here we have 2 multiplied with minus and multiplied with 7, so we have minus 14 sine 7x. And this is our final answer. Now number 4, we have to find out the differentiation of tan x using the quotient rule. Now if you remember the quotient rule from my third video, we had v multiplied with the derivative of u subtracted with u multiplied with the derivative of v and whole divided by v squared. So in order to find the derivative of tan x, we have to first express it in terms of its quotient, which is ddx of sine x divided by cos x, which was one of the most important trigonometric identities. So applying the formula, we have cos square x at the bottom, then cos x multiplied with the derivative of sine x subtracted with sine x multiplied with the derivative of cos x. And so we have cos x multiplied with the derivative of sine x, which is also cos x, minus sine x multiplied with the derivative of cos x, which will be minus sine x divided by cos squared x. So simplifying, we get cos squared x plus sine squared x, as minus 1 multiplied with minus 1 is 1 divided by cos squared x. Now if you recall the trigonometric identity sine squared theta plus cos squared theta, which is equivalent to 1. So we have 1 divided by cos squared x, which is exactly equals to sec squared x, and thus we can also find out the derivative of tan x using the quotient rule in this way. For the last math, we have sec 4x plus cosec 5x, and if you remember the derivative of sec x, which is sec x tan x, and for cosec x it is minus cosec x multiplied with cot x. So differentiating, we get sec 4x multiplied with tan 4x and then multiplied with the derivative of 4x. As you assume that this whole thing is sec x, so we have to multiply with the derivative of the inside function, which is 4x, plus the differentiation of cosec 5x, which is minus cosec 5x multiplied with cot 5x and multiplied with the derivative of 5x, as we are using the chain rule. So finally we have for sec 4x tan 4x minus 5 cosec 5x cot 5x, and this is our answer. So thank you all for watching this video. Please give a like, comment, share and subscribe, and see you guys in the next video.